Hi everyone. We'll be waiting 2 to 3 minutes before starting the webinar to accommodate for the rest of the attendees who are in the middle of connecting. And while we're waiting, we're asking the Paul Levy question. If you could improve one thing in Azure Sentinel, what would it be?
Well, we are perfect. That's great.
Yeah, I was thinking the same. But let's see. So just to remind, you can either use the link provided on your chat or at the very top, you'll see paulev.com/security webinar. Over, I'm thinking the folks want to save the best for the end. So
No, there's some issue. I tried. I submitted something and it didn't work for me.
it didn't work for you. That's interesting.
Yeah. So I actually submitted one, and so maybe others are trying as well.
There you go.
Anyways.
There you go.
Oh, I see. It was the other one. I see.
Okay, good.
So everybody, thank you. We were just missing you all, but you were there.
Okay. Well, welcome everyone. Thanks for joining us, and thanks for being a part of our community. My name is Valentin Kolika, and I will be your host for today. A few reminders before starting. If you have issues viewing the stream at any time during the presentation and are using the web browser version of Teams, please just refresh your browser. Or if you're using the desktop app of Teams, please exit and rejoin. I see some glitches. So, can you still see Ofer?
I presented.
Okay, perfect.
I took over.
Okay, got it. Please note that this webinar is being recorded and it will be shared publicly. We will post the recordings on our security at aka.ms/security webinars. Closed captions are available during this live broadcast. You can enable it by clicking on the CC button located at the lower right corner of your screen. During this time, please feel free to ask questions at any time by typing them in the live event Q&A by clicking on the Ask a Question button. Be aware that any questions you post will be publicly visible. However, if you prefer, you can post your question anonymously by checking the box right below where you enter it. Now, we often get many questions on these webinars, and we will do our best to respond to all of them in real time. In the event if the answer was not provided, or if you may have additional questions post this event, please don't hesitate to raise them on our Azure Sentinel forum at aka.ms/Azure Sentinel community. I will be posting these links here shortly in the chat room. We love to hear your feedback on how we can improve these webinars. And you can do so at aka.ms/security webinar feedback. And while you're there, please join our community by visiting aka.ms/security community. This is the best way to ensure that you don't miss any future webinars or major announcements. On our community, you can speak directly to our engineers and that in fact create our security products. You'll be able to influence our product designs and get early access to changes by doing things like participating in private previews. You can sign up for that at aka.ms/security private preview. And while you're there, you can request features. You can give feedback, review our product roadmap, attend in-person events, or join webinars like this. We believe that the best way to improve our products is simply by removing any barriers between you and the people that create them. So we hope you'll join us. Today, Ofer will take us through optimizing Azure Sentinel KQL performance queries. This will be the part 3 of KQL series. And if you missed the previous 2, you can find them at our aka.ms/security webinars. Ofer Shazaf is our principal program manager and with our Azure Sentinel team. And without further ado, I'll turn it over to Ofer. Ofer, the floor is yours. And we're actually putting a face of yours today, so
people can recognize me in the street if we ever get to travel.
Exactly.
Thank you, Valon. As Valon mentioned, today we are talking about optimizing KQL. It's a deep technical topic. I hope that you'll bear with me. I hope that I'll make it useful and not boring enough. There is a bit of a university lecture atmosphere to the talk today. Apologies in advance. As Valon mentioned, this is part of a series, our ever-growing Ninja training. I think this is module 7B. Specifically, your journey through KQL will take you through, by now, a lot of stuff. And I hope that you'll find it easier to learn how to use our query language, which is common across all our modules. You'll start from a plural site course, that's the basics. And then we have Ninja training, which is a hands-on lab, enabling you to actually experiment using available online service. And after you do that, and after you learn how to optimize KQL, it's time to learn how to use KQL in Azure Sentinel, for example, for writing analytics rules, or for creating workbooks, or hunting, etc. But today, we are optimizing KQL. What will we learn today? I have a missing slide here. No, it's the next one. I skipped over it. What we'll be learning today. So first of all, we learn how to understand what is your query performance. How do you know whether a query took a lot of time or less time, and how much? We'll touch a bit on Cousteau. Cousteau is the data store used by Azure Sentinel to understand. So the optimization guidelines are not just black magic, but there's some reasoning to it. And then we go into basic guidelines. Guidelines? God, I was tired of writing that. I'll fix it later. In order not to make it too boring, after talking a bit in abstract about guidelines, I'll go into examples that would make it much more useful and will show additional elements of optimization. But the first question is, why should you optimize in the first place? It sounds logical. We always want to optimize. We want to do better. In practice, there are two main reasons. First of all, for any interactive use, you'll just save time. If your workbooks are dashboards, or your hunting queries, or your search queries are faster, the user, yourself or user you prepare it for, will wait less. A workbook, for example, can contain a large number of queries, and it will draw faster if the queries are optimized. Additionally, there is a timeout. There is a limit to how long a query can run. You may know that you don't. We pay for queries, not you. The pricing metric for both log analytics, which is the underlying service, and Azure Sentinel, the security solution on top of it, is by the data you ingest, and you can run as many queries as you want, as often as you want, and in as many models as you want. But they are costly. So in order to make you optimize, there is a limit. It's a high limit. It's not easy to reach, but it is there. And you need to make sure you are well below it. So how do you know how fast is a query? So when you run a query, that's just an example of a query in the. By the way, I need to say something. I forgot to mention that this is part 3. If you don't know KQL, it would be harder today. If you never used Sentinel Log Analytics, the webinar, by the way, applies to Log Analytics just as much. It'd be hard to follow. Sorry for that. I'm not going back today. I'll try to make it useful.
Hey, Ofer, real quick, sorry. Can you just stop sharing, because I'm having a hard time to actually put your video on the go live. Okay, stop sharing, and then there you go. Now share again, please, if you don't mind. I'm sorry. Just trying to put.
No, it's fine, guys. I asked to once for a change be visible. And if it didn't work this time alone, no worries. I'll share a picture of my own in the deck when I send you.
Yeah, go for it. I don't think it's working, but I'll have to check it out later. Thank you. Sorry for interruption.
Okay, so as you can see here on the top right side, we have the time that the query ran. This is an approximate. It's helpful, but there's more accurate information available if you press this one. If you press this small arrow, you'll get a whole tab showing information about the query. The only one that we'll actually focus on today is the total CPU time for the query. This is one that I used and that we'll see throughout the presentation today. As sort of a scale, the numbers are in milliseconds. So I wrote here more than 100 seconds is excessive, but what you see here is 46 milliseconds. So excessive would be 20,000 times more than that. And you know, 20, you'll look at 2,000 times. And more than 10, the 1,000 seconds, which is 15 minutes, I believe, is maybe throttled by the system. I mentioned a timeout. So we are well below that. All the numbers you see today are below that, but there is a limit. That said, testing is not that simple. Why? First of all, you may get very good results even if you don't follow best practices. Whatever I'm talking about today, queries are highly optimized. So even if you write very badly, the system does work for you. It also caches information. You'll see in some of the queries that I present later on that I try to break optimization intentionally to the worst of things. That's why the example below tend to be extreme. Real life may not be as extreme as that, but in order to show things, I was really into the extreme. For example, one way to ensure that things takes more time is to ensure no results. It ensures inconsistency. All failed. Actual results may depend a lot on how many results are actually retrieved in each step of the query. Also, keep in mind that when you do interactive queries, which you usually do when you measure performance, the results are limited to 10,000 items in the viewer. And as one of the optimization methods, of course, the engine will stop after 10K results. So if you have a big query over millions of records, which in real life would serve something, you do some summary, some analytics on it. If you don't do that, the query will stop after showing 10,000 results, which is usually very fast. So testing is not easy. That said, after experimenting a bit when preparing for this webinar, I was always able to avoid most break optimization for the sake of understanding. So after we learn about understanding where to read the timing figure, let's understand Cousteau, the database that we are working with. Cousteau is a columnar database. There's a lot behind it, but I'll focus on the things which are of importance. The most important aspect of Cousteau for optimization consideration is that data is stored in extents, small files or pieces of information that usually are first can be distributed across machines. That's where the scalability of the system comes from. And also are split by time windows. Usually they may overlap because they may be written by different services, but each extent or shard, as it's sometimes called in other systems, has a very specific time boundaries. This implies that time, we'll see it later, is sort of the king in retrieving information. And if you choose your time wisely, everything will be more performant. But it's not just about time. There are also indexes. The data is, of course, indexed, as you can expect. Specifically, the extents themselves are indexed. So for each extent, we know what strings are in it. And strings is both full field values as well as keywords within the field. The keywords part is important. So words split by delimiters. We'll talk about it later when we talk about practical optimization. And for numerical values, it will be, this extent has information in this field between, in this case, 20 and 2300. So that's the indexing. And of course, time generated is a type of an index in this respect. It's the limit. How does that translate to actual optimization? So let's say we have those 4 extents. Each one of them has a time range as well as a counter value index and range. And you see that I used for example, the query at the top. Since the query checks for a counter value greater than 120, only extents on machine 2 and machine 4 are relevant. And since the time indicator selects extents 3 and 4, we find out that the only relevant extent to actually scan is number 4, which of course dramatically reduced the amount of processing needed in order to retrieve the information. This selection of extents is the basic optimization method, at least as far as filtering is concerned, which is the first element we'll talk about. The faster you limit and get to a smaller number of extents, the faster the search is. And that will be very evident when we get later. Methodical pause. We are now getting into the actual optimization guidelines.
And your webcam is live, Oprah, just so you know. People are happy to see your face.
Oh, thank you. I thought I was doing funny faces. That's why you said it. I forgot that it was a problem. Thank you. Hi, guys. So, filtering. So I mentioned everything starts with time. Therefore, it's very important to filter by time first of all. Select your time so the right extents are selected initially. Everything starts with time. We'll talk a bit about time in one of the coming slides in a more elaborate and less obvious recommendation. The other element is very specific In log analytics and in Sentinel, we cache in SSD the last 14 days. That means that search over last 14 days is faster. That's why in Sentinel, we limit the look back of rules to 14 days. In practice, by the way, in my testing, searching over longer time periods was not much slower as long as you optimized well. So it's not as if it stops, it's not cold storage afterwards. But even though it's written cold storage here, it's not really cold. I should call it probably warm. So it's warm storage afterwards. It does affect, and of course, the more time you select, it's pretty linear. The speed, the query processing time. So if you can limit time, it's better. That said, you can search for longer, and if you need to search for longer, it's very important to follow the rest of the guidance. The next sort of rather obvious guideline is to filter fast. So to make sure that you filter and get as little records back as soon as possible for your own logic. So I used here a pretty extreme example that I mentioned. In my information set, the word offer was not relevant, of course, because it was an event stream and my username is not offer, so nothing relevant. The word allowed was actually pretty common. It was part of one of the messages. So the first query here returned very fast because it had to count a very small number, a 0. While that next one did a lot more work. Actually, I was surprised by the difference here. It's a bit more than I expected. This is an extreme example. The second one, on the other hand, is a more typical one. I actually used an interesting way to search for Windows event IDs. Activity is a string that has the event ID and then continues with the event description. So I used start with, which is actually very performant. It's actually better than equal in many cases. And you see that when I looked for event number 4699, that's very rare. It was 3 times faster than when I looked for event 4625, which is very common. So you may need to look for 4625, but in many cases we have multiple conditions and you want to start with the less common one. For example, and that's a very important example that I encounter a lot, I see many queries that start with exclusions. Exclusions usually reduce little and they are very costly in terms of running over all the records and just checking if a whitelisted user is not part of them. You should wait to the end to exclude. It's not intuitive, but it's very effective. Do your magic and then exclude at the end. After we talked about filtering fast, we have to touch on operators. Probably the biggest mistake that people do and the easiest one to fix. The most common operator in string expressions I see is contains. Contains is easy because it usually addresses well every use case. Contains implies a substring. The word offer appears anywhere, not the word, the string, the character sequence OFER appears everywhere in anywhere in the message field. However, contains does not use indexing. I've mentioned before that text is indexed by words. So the operator has searches for offer as a word, which means it's delimited. In some cases, you really want contains, but in many other cases, you really are looking for a word, for a phrase. So has is a much better choice. Notice that the difference is amazing. So it's a very, very common mistake then. A few additional elements around that, beyond that. First of all, equal when relevant is the best, but that's only for specific use cases. Case sensitive versus case insensitive do not matter much. I've seen different advice in different articles. My experimentation shows that using a case sensitive versus case insensitive operator does not matter much. Start with, as you may expect if you had your computer science classes, it uses indexing as well, so it's even faster than has. It's a very, very efficient one. That's why in the previous slide I actually used start with rather than has. End with, on the other hand, surprisingly, is non-indexed, and it's just as bad as contains. Lastly, a bit surprisingly, a simple regular expression match is as good as contains. So if you need regular expressions, you can use them. They're just as expensive as contains. But regular expressions are sensitive to the actual regular expression. The second one that I had in here is a complex regular expression and took twice as much, nearly twice as much, as a simple regular expression. And I won't even get into the no-no of search, which is just so expensive. Search, in essence, is has, but over any field in the event. Nearly never you need to actually search in every field in the event, and the cost is extreme. All that was between intuitive to things that are clear once you understand indexing. The next one is where things become interesting and I see a lot of mistakes. And if you look at the difference between a number here, it is important. As long as you use native fields, things are fast. Once you start to use calculated fields, those that are the result of the extend keyword, things get much slower. You lost. It's now not part of the extent selection. It's only once the information was received, it is analyzed, usually in a full scan. And you can see that when I did this trick is extreme because I really tried to make things work badly. I did a new variable called m. I assigned to it message plus offer, and I searched for non-existent text in it, and it took ages. By the way, ages is not really a lot in this case. It's 174,000 milliseconds. It still is 3 and something seconds. But it's way, way more than if I would have selected the original one. A more typical example where the price you pay is not as big is the one at the bottom. You see that the first operator is case insensitive. In the second one, I force case insensitivity by using an operator and changing the value, not using the original value. But I lost the use of the indexing, hence the big difference here. So, if possible, always use the original fields. One thing that we'll see later on in one of the practical examples after I talk about the right boring guidelines is pre-filtering. Sometimes you need to work on calculated fields. Sometimes you need expensive operators, as we saw in the last slide. But in many cases, you can pre-filter. You can reduce the number of events considerably before you get to use the expensive operators. And we'll see an example later on. Oh, that's actually interesting. You see that in the last example here, actually, I have an extend and I assign M to a message, but I did nothing. So the system did optimize, and using a calculated field did not cost me much. Moving from worse to even more extreme, I want to show something. The example is telling, and it's as most of the examples here on the extreme side, so I can get you amazing large values, but it does teach on a lot of things. And there's a lot to learn from this one. I used here join. First of all, join is more expensive. It means that two tables have to be correlated and matched, in this case, between two fields, source IP in one table and IP address in the second one. Now, the first one used the UI filter that's available in the log search field of 24 hours. So matching those two tables for 24 hours, there were no results, by the way, no matching IP address in my case, took 17,000 milliseconds, so 17 seconds. Overall, not that bad. Now I wanted to reduce and I wanted to check for 1 hour. My assumption was that I'm changing on the first one because the number at the top, the screen was still 24 hours. And I did hit on a much lower number, which is great. But when I checked into it, I found something interesting. And that's something that actually I learned about when preparing this webinar. And it is important. It's the first time. There'll be a few others like that later on, where optimization is tied to actual correctness. So in the UI, what you'll actually see is instead of 24 hours, you'll see a query, time range determined in the query, something like that. In practice, you'll find that the time restriction of 1 hour that you assigned here to the common security log was applied also to the security event table on the other side of the join. This is implicit. That's not clear from the UI, and you need to be careful about it. The most important aspect of it that you need to add to your guidelines is every table always needs a time condition explicitly. It's good for performance. We'll see that in a second. It's good for correctness and to ensure that there is no optimization you're not aware of. So I tried the other way around. I tried 1 hour just on the second table. And I got something amazing. I got, well, 522,000 milliseconds. That's 500 seconds. That's a lot. And when checking why that happened, I found something which may qualify as a bug. When I did 1 hour on the second part, the first part was considered without any time limitation, and the entire table, the entire history was actually searched. Now keep in mind, this may change the actual results of the query. Again, what you really want to do is you want to make sure that you have time conditions on both. Now, what I wanted to do in the first place when I started with example number 2 here was to do common security log for 1 hour and then security event for 24 hours. I wanted different times. So what I got here was actually correct by now. I had time on each one of those, but it took quite a lot of time. What I added in order to make things faster is that I switched between the tables. I moved security event to be the first one and common security log to be the right side of the join. This is an optimization rule that's very important and not related to filtering, but it was here in the example. So keep in mind, when you do a join, the left table has to be the smaller one for performance, not for correctness. Notice the difference between 70,000 and around 1,000. It's extreme. It's exactly the same query. It reproduces the same results. So a bit of summary of what we learned so far before we get to more interesting content-based examples where it's not just synthetic queries. So we learned that you need to start with a time filter and if possible limit to 14 days. You need to filter early. If less results are received in the following stages of the pipeline, performance is much faster. You need to use performance filtering operators, and we saw a bit of which ones those are. And I didn't present it yet, but if not possible, if you cannot use, if you need to use slower operators, you may want to pre-filter, and we'll see an example later. And we saw that you need to filter on native columns rather than calculated columns. And sorry for the typo here as well. I'll touch on the reduce guidelines in the next few slides, summarize early and project explicitly. We did see that you need to have the smaller table on this left side of the join. And the last three we'll talk about later on. So that's an initial summary. We'll get to the checklist again at the end of the presentation and discuss also the non-bolded ones. Okay, so after I showed so many synthetic queries that were just used to get extreme results, I'll show you real useful queries still with extreme results, which is interesting. And in this case, you actually get a bonus. I'll teach you how to do geolocation in Sentinel, which I don't think I did before, so something to learn. So the starting point, still nothing to do with optimization, is that we need to get geoinformation in Sentinel. The easy way to do it would be using the external data operator and getting a file. It's Maxmind free to use a geoinformation file that's available in the URL here. And using the expression we see here, you get geodata to be the table that contains the information. Two things to note about it: it's pretty large. It has 172,000 records. And that the data here is not IP addresses, because then it would be a lot more than 172,000, but rather CIDRs, so networks. And each network has a geolocation attached to it. The next step would be to do a geolocation query. The way the query works is, first of all, it's a heavy query. So we do a time filter. I select 12 hours here. I use 12 hours and 24 hours over my data set in the following time measurements. There is then a pretty heavy calculation. MV-apply, to those who don't know, is essentially a way to do a loop in KQL, and it will go through every element in the table we just saw, the whole 174,000, and compare it to the caller IP address in every event. So it's a Cartesian multiplication. It's a very large number of iterations. But it works. It actually provides with results. But the time is horrible. You need 60 seconds for the 12 hours that only have 300 events. So it works, but it's very slow. And if you take it for 24 hours, in my case, the number of events was not very large, you get to 90 seconds. It's useful. You can do less than 12 hours. Your rule might run every 5 minutes, so it might work for large data sets. Still, optimization is really called for here. How we will do that? So an obvious option is just to filter early. I mean, you have some usage. You are using the geolocation for something. So if you'll filter for the events you really need, you'll get a much lower number of events, and timing would be much better. Now it's 8 seconds linearly for 21 events, but it's still just 21 events. So I didn't optimize, I just was more selective. It is useful. Sometimes you don't keep in mind, filter early, as I mentioned in the guidelines. But let's look for something more impressive than that. What I'll do now is I'll use summarize by caller IP address. If you think about it, all I do is I need to look for the geolocation for each IP address, not for each event. So if there are repeats, if there's more than one IP, if an IP address appears more than one in the data set, I don't have to look for it twice or more than that. So we can do summarize by caller IP address, and the rest stays the same, which is pretty amazing. And the results are amazing. I go to 765 milliseconds for 39 events and a bit more than 1,000 for 420. If you remember, the numbers before were 60,000 and 90,000 respectively. When I tell people to do that, they think I have a magic wand. Now, the interesting thing is that the improvement is a bit too impressive, because the number of events I had here is 300. The number of IP addresses is around 30. So it's actually only 10 times as much. So why was the time reduced in nearly 100 times rather than 10 times. That requires investigation. And that will show us another optimization capability and requirement. So I did something interesting. Instead of doing here a summarize, I did project. What project does is that it leaves in the dataset only the relevant fields after project. So this actually is exactly similar to the first example. We still examined 300 events. We reduced nothing. The only thing we did is that going into the loop, we have lighter events. And the results are pretty impressive. It's, if you think about it, we started with 60,000 and we ended with around 700. So that's 10x and that's 10x. So what we've learned is that summarize, as you would expect, since we got 10% of the events to look up, we're moving from 300 events to 30 IP addresses, did as expected and reduced 10 times the amount of time needed for the query. But what's more interesting is that when we were selective, when we reduced the event size using project, we got another tenfold decrease. And that's a very important lesson. Now, it's not an easy one to learn otherwise, because in most simple queries, the system optimizes itself. So if you don't have joins and MV replies and sophisticated stuff, KQL knows that you summarize at the end which fields you need and will drop very early the unneeded fields. So optimization, if you try to do project in a normal query, you'll get nothing because the optimization worked for you. This query, which is a real world query and it's really useful, is more than optimization can handle and shows us a very important lesson. We need to reduce the number of fields explicitly, just as we need to always do time condition explicitly. And the improvement is very, very significant. Lastly, this is less about optimization. It's more about being, completing the picture. In all the examples I showed you so far, I did data reduction. I essentially found IP addresses and their geolocation. I threw away, when you look back, when you'll have the copy of the presentation later on, I threw away the actual event data. And the question is whether that's how I got performance improvement, or whether I can do a query that is just as performant, but actually keeps all the Azure Activity events with enrichment information. And the answer is you can do that. So here, what I did was juggling with joins. Actually, I added one join here in the middle that got me back based on the caller IP address that were looked up in the lookup section above. They were attached to the Azure Activity table. So I have the Azure Activity table, and I join it to the caller IP address and get with each Azure Activity record the CIDR that it belongs to. And then I reach with the rest of the geolocation information. The result here is a full Azure Activity event log, the whole 300 or 420 events in my dataset with geolocation. And the timing is still very good. So optimization was not data reduction required. Interestingly, when I did this exercise, when I built it, I forgot this. And I already told you, you always have to do a filter by, actually, I forgot this. You always have to use a time condition because it's not explicit in more complex situations. In this case, when I didn't do this phrase, I got the all Azure Activity table, and since I used write outer means take all of the Azure Activity table and match it to the relevant geo information, I got millions of results, which I didn't expect. I expected exactly 300 results. So again, correctness-wise and performance-wise, always make sure that for every table in every join or multiple table query, you assign a time condition. The last element here is actually pretty important. It did not change performance in this example for me. It should enhance performance in some examples, but it's very important for correctness. I used let a lot in my queries. Something to know about let is that it's syntactic. It's just a macro. Essentially, when you do a let statement, it means that whenever lookup appears in the query, it is replaced by whatever is here. But the actual execution is done twice. So if I have here lookup here, and then I have actually lookup, I have just one, but geodata. I have geodata. Too much information that you have here. So I define geodata, and it appeared twice. It will be run twice, not just once. And the same true for events. Events and events twice. By using the word materialize, I ensure that the let statement actually caches the results. This potentially has a performance improvement effect. Not in my example here. It also ensures that the data is more correct, because while the geodata does not change over time, events change over time. So two runs which are not exactly the same moment may produce different information. So I hope you got value from the geolocation example, both about how to do geolocation as well as into the extreme optimization it requires. It was really example of where optimization is really important. The second example, real world example I want to discuss is parsing. Parsing is a very common use case for queries in Azure Sentinel. You do it all the time. You get data, and the fields require a way to extract values from. Syslog is a great example because Syslog is essentially unparsed. You get messages, and you need to extract data from them. So the first way to reduce parsing is expensive. The operators usually do not enjoy indexing, and they cost performance. The query as presented, which includes this line, which does pre-filtering, I mentioned pre-filtering, took around 2000 milliseconds. Without the pre-filtering, it took more than 10,000. It's an example I promised to show you before, where if I used extract, which is a parsing operator that is costly and does not use indexes, if I know how to pre-qualify it with a cheap to run condition, I can shave a lot of time from the query. It's a very useful technique whenever you need expensive operators, and parsing operators are a very good example of that. Continuing on this example, rather the same one, we have a number of possible parsing operators. I see the use of extract a lot of times because it's sort of the easiest. You just extract every field one by one using separate regular expressions. And I specifically created this one to show you that's not the right way. There are two additional options that can do just the same. One of them is extract all, which just uses a single regular expression to extract all fields. And the other is parse, which is a more featureful option. In this case, I even didn't use regular expressions. I used simpler parsing. Parse does support also regular expressions in a single extraction method. The expectation I had, and it proved right, was that because the first use of extract requires 3 passes for each string, while both parse and extract all requires 1 pass through the string, the 2 latter ones will be more efficient. And we'll see the numbers in a second. I do want to show you that I had to add this line here to force no optimization. Because if I did not use the fields, they were not extracted in the first place. So I needed to use them in some way, shape, or manner in order to make sure the numbers are representative. And the results are, and by the way, if you missed, I did pre-filtering as I showed in the previous slide. The results are extract took around 40% more than the other two. And I checked with 3 parameters. Many parsers take a lot more than 3 parameters. We'll see 1 parser in the next line. So if you have 10 parameters, parse and extract will even better. There's an interesting number here which I didn't explore further, and that's that with pre-filtering, while with no pre-filtering, parse and extract were the same. With pre-filtering, parse was better. We suggest that parse is more costly if it fails, because pre-filtering ensures no failure or less failure. Lastly, there's another operator that I did not look into, but it should be even better than parse or extract all split. It just doesn't fit every case, and it didn't fit this case, so I couldn't add it. Now, this is parsing as part of a query. Very importantly, Sentinel uses stored parsers. Stored parsers are larger query. You see here a very bad use of many extracts, and that's actually one which is on our GitHub, and we need to fix based on my research today. And then you save it as a function called screed logs, and then you can, your user or yourself can always use screed logs and have all the fields available as part of the query naturally. That's our parsing capability. So stored parsers are a very important building block of Azure Sentinel. However, they can be expensive in performance. And today we'll talk about how to make that better. For example, we issued a very nice to use parser called additional extensions parser for common security logs, which takes all the additional extension string field and split it into fields. It's so easy to use and it's so useful, but it's very, very slow. It's actually too slow to be useful without the trick I'll show you later on. The reason is that if I'll go here, when you use the stored parser as the first element, you missed on all the optimization discussed so far. You didn't filter even according to time prior to using it, unless time is part of the query definition in the query window. What do we do around that? We use a new feature that was introduced in Local Analytics Sentinel around 2 months ago, and it's called parameter functions. I took the same parser, the exact same parser that we published on our GitHub, and I wrapped it in a definition of a function, a parameter function, rather than a regular function. You see that the parameter for a function is a table, and I need to explicitly define every field which I'll be using here. You know, that's not the one which I'll be using here. By doing that, I enable using the following syntax. So I can start with a common security log, as I used to. I can run any pre-filtering I want, and then I can use this syntax to run the parser. And then count is, of course, pretty stupid here, but do whatever I want later on. In this way, I can use parsing. It's a bit less implicit. You need to know to start from the right table and parse at the right stage. So it's not just use a different table, but get wonderful performance improvement that makes parsing relevant. Now, today, this will change over time. Today, you cannot just write that. I use the let statement. You cannot just save a parameter function in the workspace as you can do for regular functions. You need to use a PowerShell, which is linked from here, and it works very nicely. So we're toward the end. Let's summarize and go back. Now we have all of them covered, I hope. So getting back to where we started, always start with filtering by time. And I don't know if you read it elsewhere, but filter by time every table, even if you have multiple tables using joins or unions or whatever. If you can limit to 14 days, it's faster. Filter early and fast. For example, include before excluding, defer exclusion to the end, because the smaller the number of records that move to the next phase in the pipeline, the faster the query will be. Use performance filters that hit on indexes. Has, start with are very good. Contains is much worse than that. If you cannot use it, you may want to pre-filter. A great example would be regular expressions. If you do regular expression matching or parsing, you can usually pre-filter using a keyword using has and gain a lot of performance. And lastly, around filtering, use native columns rather than calculated columns. And again, if you need to use the calculated columns, sometimes pre-filtering with the native columns does help. Now, the next two ones are a lot less intuitive. You saw them in the geolocation example. Summarize early. It's a great way to reduce even more than filtering. In many cases, you don't need to process all data. You need to process a summary of the data. So summarize as early as possible. And while in most cases, reducing the width rather than the number of events, so the size of each event is done implicitly as part of optimization. In more complex queries, it is not. So try to project and limit the number of fields from the event that are moved to the next stage in the pipeline. We saw in the geolocation that it was just as effective as summarize. Tenfold increase from this one and tenfold increase on this one. We did touch is a whole topic by itself on using the smaller table of the two on the left side of a join, and we mentioned that materialize will cache tables, so it will make sure that subqueries are run just once. And when we got to parsing, we mentioned that split, parse, and extract all are much better than the multiple extracts. It's a very common mistake. And lastly, we got into the more complex area of using parameter function parsers instead of regular function parsers, enabling pre-filtering with parsers. So guys, that's all for today. I didn't cover everything. There are additional areas that probably worth a blog post. I'm not sure we'll get to a webinar on those. Effective JSON parsing, very important. And the last one is conditional parsers, a topic that I want you to be aware of. When you do a parsers, many times there are different types of events with different parsing requirements in the same table. And how to do that effectively is not trivial. We many times use union. So we union different parsers together. This is probably not the most performant way, and there's a way to use case, which I'll find the opportunity to discuss with you. So with that said, I'm going back to Valon to get a few questions if there are any.
Thank you, Ofer. Let me just share the poll everywhere so the folks can directly submit their questions. I did enter there the most upvoted questions from the Q&A, and I guess we can start with that.
So I have a different opinion about the take lines item. The 10K line items is the interactive limit. So that's what displayed. And I'm not sure there's anyone who can use interactively 10K line items. So any meaningful query that's used in a rule or that the user has to inspect has to summarize somehow in some shape or manner. So I tend to think differently about this restriction. One thing to keep in mind is that the API allows up to 500,000 records. So by just using the same query using PowerShell, if you want to output to a CSV file, for example, which might be what you want because a system will a smaller I assume that you want very large number of items because you will want to automate using them. So using PowerShell, you can get up to 500,000 in a single query. So that's probably the most direct answer to your concern. If in the interactive world you need more, it's worth discussing the query and what's the use case for showing a person such a large number? As to the second question about right joins, I don't know. I didn't investigate it. I did add 2 links to the presentation at the end. I sort of jumped over that go beyond what I said today. They're not as descriptive, but they may have information. There are also ways to optimize joins where there is no small table. And you are referred to those documents to see how to use hints to the engine to tell them how to best optimize join operations. Thank you for whoever mentioned that you can get more than 10K results in Excel. Yes, so to the question about materials and let, yes, materials create a variable or a table with the results of the query that is reused whenever the let assigned query is used, while let without materialize will just rerun the query whenever the name is used. So thank you all. I hope you've enjoyed this one. Oh, there's another question. Priorities and retention times for priority. So to the question about hot versus cold versus warm and the 14 days, no, our service is fixed at this optimization. We are considering in the future to have dedicated clusters that enable customers to optimize more parameters of how the system runs behind the scenes. It would require very large customers because it would be a dedicated cluster. By the way, very good questions, all to the point, all exactly on the. So thank you for being with me and being attentive. And with that, since we are over time, I'll let Valon summarize.
Thank you.
Thank you.
Thank you. So just some quick reminders since we're over the time here. Please visit us for the next scheduled webinars, whether that's Sentinel. We have some more security projects coming in, network security. We have Azure Security Center coming up, all in aka.ms/security webinars. And in case we missed to answer your question, or if you have additional questions, as usual, you can visit us on our Azure Sentinel forum at aka.ms/Azure Sentinel community. I would like to close this webinar by thanking Ofer for yet another fantastic presentation. And thank you to the rest of the team who helped answering the questions. And most of all, I want to thank all of you for being part of our community and for joining us on webinars like this. And we hope to see you next time. Goodbye.
Thank you all. Enjoy.